Next transformation we'll look at will be some constant added on to the end of the function, the d transformation. Back to our base function sine of x. If I look at the graph of sine of x plus 1, I see the entire graph has been shifted up 1 unit. Any point that I pick on the red graph, if I go up by 1 whole unit, I'll land on the green graph. Whether it's right on the middle line, or if it's a valley, up by 1 takes me to right there, or a peak up by 1 will take me there. Every single point on the red graph, if we increase it by 1, we will create the green graph. That is the result of this d transformation, some constant added on to the function. Here it is shifted up 3 units with a plus 3. If we subtract, we'll accomplish a downward shift. Here, the graph has been shifted down 2 units. Next transformation will be the b transformation, when we multiply directly to our variable inside of the function. Previously, this would accomplish some sort of horizontal stretch and compress, and also it worked opposite of what we might expect, whereas with the a transformation, when we saw a large number, our graph was stretched out larger, and a number between 0 and 1 would shrink the graph. It works opposite when we work directly on the variable. So a number that is greater than 1 is actually going to compress the graph together, while a number between 0 and 1, some decimal number, it's going to stretch the graph out. Here in maroon, we've got the base function sine of x, and in green, sine of 2x. Now we're on to this idea that it's doing some sort of horizontal compress, but we can see it a little bit more clearly. I'm going to go back and just look at 1.1x, and I'll increase this factor, this coefficient of x inside the function, to 1.2, and so on. And you can see that as that number increases, our graph is being compressed closer and closer to the origin. There we are at that sine of 2x. Here's sine of 3x. I've seen it compressed together even further. And if I think about how do the points move, what we'll see is each point on the red graph, if we divide by 3, we'll get to a point on the green graph, and we're dividing by 3 our x value. So this point right here on the maroon graph is at 90 degrees. Sine of 90 degrees would be 1 whole. And now where I get to my y value of 1 is not at 90 degrees, but it is at 1/3 of that, dividing by this factor 3. 90 divided by 3 takes me to right here, which is at 30 degrees. How about this point, and I'm referring to the one on the maroon, where we have a function value of 0 at 180 degrees. Now divide that 180 by 3 to get our value of 0 at 60 degrees. Let's just point out one more. Down here, -1 occurred at 270 degrees. 270 divided by this factor 3 means we'll see our first valley at 90 degrees. 270 divided by 3 equals 90. And there we see that function value of -1 at 90 degrees. We know that these trig graphs have this periodic repeating pattern to them, and we are interested in finding the period, which would be the distance it takes to complete one cycle. With cosine and sine, we talked about the period being 2 pi radians, or 360 degrees. That distance along the horizontal axis is what's required for us to see one complete cycle, and then we could see this piece being repeated over and over and over again. If we look at sine of 2x, which we know horizontally compressed this graph, it's going to change the period. So we're going to accomplish a complete cycle not in 360 degrees, but again divide by this factor 2. Now our period is 180 degrees. In between these 2 points, we see one complete circle. And if we're talking about radians, 2 pi radians divided by this 2 would be a period of 1 pi. So from before, we would talk about this b transformation, which is coefficient of x inside the function, as being a horizontal stretch or compress, and it still is, but now we're going to use terminology that's specific to trig functions, and we'll talk about the period. And the way it changes the period is, if our full initial period is 2 pi, we divide 2 pi by the factor b. If we're talking degrees, it would be 360 degrees divided by b. Let's take one more look, this time at sine of 4x, to see if we can confirm that pattern. So one period of sine x is 360 degrees. 360 divided by 4 equals 90. So will we see one complete period in just 90 degrees? So in between these 2 points, there's 15, 30, 45, 60, 75, 90 degrees. So we're confirming this rule that you take your period, your initial period for sine and cosine, it's 2 pi, and we divide by this factor, this coefficient on x, the b transformation. Let's include a couple other things we know about the horizontal transformation, this b transformation. When our coefficient was a number greater than 1, our graph was squeezed, compressed together, and when we choose a number between 0 and 1, we do see this horizontal stretch, and everything is now, it's still divided by 1/2, and basically divide by 1/2 is times 2. So we're stretching things out by a factor of 2. Our peak right here, which occurred at 90 degrees, now is occurring at 180 degrees after this multiply by 2. Right here, this intercept after 180 degrees, it's now intercepting after 360 degrees after the multiply by 2. And again, that's because we take those values and divide by the coefficient. Divide by 1/2 is why we're doing the multiply by 2. Multiplying the variable inside the function by -1 will accomplish another reflection. This time, it is a reflection on the y-axis. We see something similar from when we had our other reflection, that it was for us to see, actually, is this a vertical reflection or a horizontal reflection? And again, it's an idea that if we know that sine is an odd function, we'll know that reflecting horizontally leads to the exact same graph as reflecting vertically. So I want you to know that the rules from earlier transformations still apply, but with trig functions, we begin to see some effects that are coming from many different types of transformations, all leading to the same transformed graph.